Okay, welcome everyone. I have the pleasure of opening our ICG invited lab talk series that we have every month. And today it's my pleasure to introduce Lena Cibulski from Fraunhofer IGT. She's a visualization researcher there and also a PhD candidate at the Technical University of Darmstadt. And Lena is actually here for the period of 2 months, hosted by the Center of Mechatronics. And I see some of the people here. Thanks for coming as well. And yeah, Lena received her master's degree in computer science in 2017 from Otto von Guericke University in Magdeburg. And during her bachelor's, she already did a 6-month research stay at VIAVIS, the Visualization Center in Vienna. And now, as I've said, she's a visiting researcher here. So you will have like many encounters with her over the next 2 months, hopefully. And yeah, her research is at the intersection between visualization and multi-criteria decision-making. And today, Lena is going to talk about making choices with visualizations. And the floor is yours. Thank you.
Thank you. So, hi everyone, also from my side. Welcome to my talk. Thanks, Mark, for the invitation and the kind introduction. So it's a great pleasure for me to kind of start this new year of ICG Lab Talks, and I am excited to share with you some of the research that I conducted in the last years and hopefully spark a little bit of interest in the topic of how we can assist and inform making choices by using visualizations. So there are basically 3 parts to my talk. So in the first part, I'm going to talk about what it means to make a choice and what is so difficult about it. And then in the second part, I will show some real-world examples where we developed visualizations to assist domain experts make informed choices in different applications. And in the last part, I'm going to provide you with some concluding thoughts. So my research is centered around making choices. By that, I do not mean the trivial choices like coffee or tea in the morning, but the more complex ones where we are confronted with a lot of options and there's no objectively best solution. So think of your last holiday stay, for example, where you needed to choose a hotel, or think of an engineer who needs to choose which prototype out of many should be taken to production. So the common ground here is that each option is valid in its own way, and we need to trade off properties to come to a conclusion. And this requires human judgment. So what I find most interesting about choices is that they are inherently subjective. So they can vary from person to person depending on their education, their goals, past experiences, and so on. So a scientist who dedicated a lot of his life to investigating how we as humans form judgments and make decisions is this guy here. This is Herbert Simon, and he was a political scientist, but his research also heavily influences disciplines like computer science, economics, and psychology. And Simon is particularly known for his theory of so-called bounded rationality. And this theory deals with the idea that human reasoning is not necessarily consistent with rationality. So why is that, you might ask? Well, decision problems can be quite complex and time is often limited, as is the cognitive capability of our human brains. So as a consequence, we will not be capable of conducting a full cost-benefit analysis, and we are left with no choice but to form heuristics and seek for a satisfactory rather than an optimal solution. So to describe how we as humans make decisions, Simon came up with this 3-stage model that you can see on the right. It was already introduced in 1960. But it is still commonly used by researchers today, so 60 years later. In the intelligence stage, the individual identifies a condition that calls for a decision. Then the design stage is where different courses of action are invented, developed, and also analyzed. And then one of these alternatives is finally chosen in the choice stage. And then sometimes people add a fourth stage to this model where past choices are reviewed. Now, who are these individuals who make decisions? So on the one hand, there are professional decision makers, so experts whose job it is to repeatedly make decisions in their field and who are trained to do so. And then on the other hand, we have casual decision makers, so basically all of us, who face difficult or complex decisions at some points in their personal lives. So for example, we might search for an apartment to rent. This is what I did when I came here. So for Linz, I found about 800 apartments we could choose from. And then typically we look for an option that dominates all others on all aspects we care about. So obviously we could filter the search results accordingly. However, we add too many restrictions, the result list will be empty simply because an option that fulfills all of our wishes most often does not exist. So what we actually search for is an acceptable compromise. And then as an example for professional decision-making, let's consider engineering experts who are responsible for designing customized mortars like this one here. So this means to specify the properties, so the material, the winding patterns, the geometry, and other parameters such that the mortar's properties optimize application-specific requirements. So expert choices typically involve a lot of expertise and experience, and this is why they are typically made on behalf of other stakeholders who do not have that expertise. But as it is not the experts themselves, but their stakeholders who are affected by the consequences of the choice, things like communication and trust and transparency are important. Now, let me tell you a little bit more about what it means to make choices. So personally, for quite some time, I found it rather difficult to find a name for that exact type of applications I was personally interested in. So throughout the years, I used different terms whenever asked what I was doing. So was it decision-making that I was aiming for that seemed too broad? Was it multi-objective optimization that seemed too mathematical? Was it engineering design, but that seemed too bound to the application domain? So I was quite happy when one day I realized that these applications already had a name in our visualization community, and this name is multi-attribute choice. So that one seemed just right to me, identifying the best among a fixed set of alternatives, where each alternative has multiple properties. Now, at the time, I was diving into the more application-specific topic of engineering design. I came across these 4 properties, which I found later to largely hold true also for multi-attribute choice in general. So first, choice is purposeful, which means that it begins with an explicit goal. So some functions or properties that the subject decided upon should perform or have. And then second, choices are, of course, shaped by specifications and constraints. So specifications tell what the chosen option is intended to accomplish, while constraints are limitations that the decision maker must stay within. Some are absolute hard constraints, but many of them are relative and must be balanced against each other and against how well an option satisfies the specifications. The choice process itself is rather systematic and can be iterative. So although there are no imposed instructions, there are characteristic steps, as we have already seen, which are repeated as necessary. So otherwise we would just be lost in an endless search for the optimal solution. And then finally, decision-making can also be a social and collaborative undertaking. So either as commissioned work, as in the example of motor design, or as group decisions, for example, in tumor boards in medicine. And in either case, as I said, the communication with customers, patients, or other stakeholders in general is crucial. So what exactly is it that makes choices difficult? So first of all, these conditions calling for choices most often concern an ill-defined problem, where it is hard to articulate how exactly we imagine the ideal solution to be. So to not overlook a solution, we usually compile ourselves large sets of options to choose from, and computing has made this very easy, even if the options come with many, many properties. And then the actual choice involves conflicting goals most often, but it is also shaped by the experience and the domain knowledge of the individual who's making that choice. And as we already saw, it relies on highly subjective preferences, which might even shift as we learn what level of performance is achievable under which conditions. So what do we need to help with making choices? My research basically touches two areas of science. So we need the study of data because the options are basically multivariate data in a large data table or some other data structure. So it makes sense to consider known ways of extracting patterns and meaning from such data. And on the other hand, I said that making choices requires human judgment. So we also need the study of human beings and how they make choices. And this most often involves the role of knowledge, cognition, problem-solving strategies, and so on. Now, one might say that decision-making is not a particularly novel topic in visualization research. However, as I already mentioned, it is important to not confuse decision-making with multi-attribute choice. So choice is really only one out of multiple stages, and this stage has not yet received much dedicated attention. So what we have are visualization approaches that help users define the importance of criteria or combine multiple attributes into aggregated scores, often for the purpose of ranking. We also have a number of visualization design studies for decision-making, both in specific application areas like lighting design or fisheries management, but also in the context of exploring solution sets in general. And then there are works that target multi-attribute choice in particular. And this research has also moved towards empirical investigation of different aspects, like human limitations, so biases, or the role of instructions. And people also started to think about how we can evaluate the effectiveness of a visualization to support choice tasks in particular. However, there are still some research gaps to be filled. So in general, my impression is that few visualization tools are specifically designed for exploring trade-offs or dealing with subjective preferences, let alone choices involving dependencies or uncertainty. And this might be a symptom of the fact that the focus of visualization research is still on helping users analyze, so find anomalies or correlations, rather than targeting choose as a task. So choice itself as a task is still not very common in current visualization theory. And in studying this type of task, we can also learn from related disciplines like cognitive science, for example. And then empirical evaluation is up to now limited rather to analytic instead of choice tasks. And if evaluation considered choices, then these are rather based on artificial settings or, well, target binary choices. So we need to study the effectiveness also on real-world choices and on people who are, in fact, decision makers. So to summarize, multi-attribute choice is an important task, but visualization research has just started to particularly address the challenges of it. So our aim is to advance our understanding of how humans could make choices with visualizations, in particular when it comes to real-world applications. So the high-level question basically is, how can we assist making choices by providing interactive visualizations? And now we we'll switch to the practical part and I will show you some concrete works. So in our visualization projects, we closely engage with domain experts and their data analysis problems. So we typically begin by studying how they work in a real-world setting and what their needs, tasks, and goals are. And for choice tasks, we are particularly interested in revealing what cognitive processes and cues are involved and what types of domain knowledge are actually used. And these aspects of decision-making are also studied in other disciplines. So for a recent project, we thought we might look into how they do it in cognitive science. So the idea is that once we understand how a decision maker uses domain knowledge and cognition to make a choice, we can design effective visualizations. But understanding how exactly domain knowledge works is difficult, mainly because it cannot really be verbalized. So we looked into cognitive science, where they research so-called knowledge elicitation techniques. And we found an interview technique called the critical decision method. So each interview consists of 5 steps that walk through an incident, so a domain problem basically, multiple times. So here we select an incident where an engineer has been given the task to design an efficient water turbine. In the incident recall, the engineer describes the design of the turbine from beginning to end. And as interviewers, it is important to really focus on understanding the story and to interrupt as little as possible. So then the interviewers reconstruct the described process in the form of a timeline. And this timeline contains both events, like a data point being highlighted, and subjective thoughts reported by the participant, like, I consider this an outlier. And then in the next stage, some of these events in the timeline are classified as decision points. So some of them are obvious from verbalization. For example, the engineer said, now we want to start the simulation. And others include subjective assessment. For example, this shape looks like an anomaly, but we can safely ignore it. And then afterwards, and that I find particularly interesting about this method, is that the interviewers retell the timeline they constructed to the participant to uncover potential inconsistencies. And then finally, the identified decision points are probed in more detail. So there we ask questions like, what was your goal? Based on what constraints did you exclude this option? How do you know what parameter to adjust next? And then together, these stages really help reveal the cues, the judgments, also the contextual effects that play a role when approaching a domain problem. So the results are then represented in the form of 2 artifacts. So the situation assessment record is a structured representation of how the incident evolved, together with goals, options, cues, and so on. And then as a complement, we have a table which specifies for each decision point what particular decision was made, why it was difficult to make, how it was made, and what information was helpful. So to summarize, we found the critical decision method quite promising because it provides a systematic way of eliciting different perspectives of domain knowledge. So it reveals different types, like the engineer said, we usually trade 2% less efficiency for fish friendliness. And it also highlights cues that steer the expert's attention. For example, too much curvature in the pressure lines. So all of this does, of course, not mean we have found a way to formalize tacit knowledge, but we think it helps us design problem-driven visualizations, in particular for choice tasks. So the understanding we gain by studying the domain experts in real-world settings then informs the visualization design, which is about finding ways to effectively represent options, trade-offs, and their effects, and make them accessible to exploration. So in the following, I would like to introduce you to 2 projects where we develop visualizations to help experts make choices as part of their daily work in motor design. So actually, as was already introduced earlier for both projects, I collaborated with researchers from this campus. So a few years ago, I met a mechatronics scientist at a project meeting, and we started working together. And he is with the Linz Center of Mechatronics. So maybe some of you already know it, at least the domain experts sitting here. They are located right in Science Park 1, so only 2 buildings away from here. And they are an engineering research company at the intersection between science and practical applications in industry. So our collaboration started out with the development of PAVED, which is an interactive parallel coordinates visualization that helps the engineers learn what level of motor performance is achievable under which conditions. But then during the evaluation, the RCM engineers told me that, well, this is useful already, but what they need to decide upon are usually interacting mechatronic components. So we adapted PAVED towards another parallel coordinates technique to allow the engineers to also take into account the mutual effects of component choices. So these are the 2 projects that I would like to show you in more detail now. So again, let's consider the problem of motor design. So simulation and optimization are used to try out hundreds to thousands of slightly varied design options. So in our first conversations with the engineers, we realized that finding a suitable compromise is highly exploratory, where this large number of design options needs to be balanced with respect to multiple criteria. We found the expert's workflow to be most similar to what decision theory calls the elimination by aspect strategy, where options are filtered into acceptable and unacceptable regions until the final choice remains. And finally, as we already heard earlier, motor designers also need to be able to justify their decisions in front of their customers. So these are 2 of the visualizations that the engineers use to view the optimization results. So we as visualization researchers noticed that their use of visualization and interaction was already quite advanced. So brushing works across scatter plots, and the brushes are even linked to the histograms that depict the underlying design parameters. And based on our observations, we modeled the engineer's decision-making process by taking tasks from existing taxonomies in visualization literature and mapping them to the engineer's workflow. So these steps are usually addressed in chronological order, but the decision process might, of course, involve going back and forth between the stages. So for a comparison, I put the decision model by Herbert Simon to the right. So these 2 models do not align perfectly, but our stages loosely map to the steps in Simon's model. The communication need we identified, however, does not appear as such in Simon's model. So coming from what we learned about how the engineers work, we defined 4 higher level design rationales, where blue indicates the property that we prefer. So the most relevant properties for the visual design were the first 2. Preferring simple over flexible relates to the user interaction, and it originates from the elimination by aspect strategy, where filtering is the prevalent form of user interaction. So we think that filtering should not demand more effort than absolutely necessary, and it is our ambition to reduce the interaction to the minimum of operations required. And for the visual encoding, we prefer a lossless mapping of design options, because it enables motor designers to visually retrieve any criterion value from any design option at any time. So after a collaboration of around 1.5 years, this visualization now helps the engineers choose a compromise, which meets desired properties both from an engineering point of view, as well as the specifications from the customer's perspective. So each of the around 170 design candidates is represented by a polyline, and this polyline connects the candidate's values for all attributes which are depicted on the axis. And you can see a small triangle indicator at each end of a criterion axis, which marks the desired optimization direction. So if you take the efficiency, it should be maximized. Now, let me show you how these parallel coordinates can be used in a quick demo. So what might catch our eye first is that the polyline sections between power loss and efficiency are crossing. So the lower the power loss, the higher the efficiency. So this is what we would expect, right? So we have an inverse relationship here, which means that we only need to consider one of these attributes for analysis. So we'll hide the power loss axis. And now you might have already noticed that each axis is actually a full axis filter already. So normally you would have to draw a selection rectangle, but here we could simplify the interaction significantly because we already know the optimization direction. So only the low quality end of an axis can be dragged to eliminate undesired options, because it would just not make sense to exclude options with desired values, right? So in the case that you really need to brush a group of options with certain characteristics, you can use a line brush, like so. Okay, so what is the most common trade-off in most decisions? Like in most cases, you have some sort of efficiency or major quality, and you have some certain costs. So this is the main trade-off. And usually you have a certain minimum required efficiency, most often probably specified by the customer. And what we can see here now is, of course, the cheaper ones are excluded now. And if we also restrict the budget, then we can see that, interestingly, these two restrictions that are now applied do not seem to have any influence on the occurrence of cogging torque, which basically determines whether the motor is running smoothly. And now we have now a certain smaller subset of options where each option optimizes all these criteria differently. So if we now investigate them in more detail, for example, we can take this candidate here with costs in the middle range, but we see that it has the least efficiency in the selection. So if we take another option, for example, that one, we can see that it optimizes both the costs, so it's cheaper, and the efficiency. But this comes at the cost of more cogging torque. And then it might be that our application requires an even higher efficiency. So we might say, okay, what about this option here? And this option is slightly more expensive, but has significantly more efficiency. Again, this comes at the cost of really drastically increased cogging torque. So these three motors are now a good example of how preferences might evolve during exploration. So if we take, if you take these two here, you can see that for what is it, €2 more, I think, you can achieve a significantly higher efficiency. So once you see that so clearly in the course of these polylines, you might be willing to invest these 2 additional euros to really achieve this higher efficiency. And then let's say this is our preferred motor variant because we have an application where cogging torque is not that critical. This option can be identified via a unique ID and can be joined with data from other environments, for example, or could be exported to start some detailed simulations. Okay, so when we collected expert feedback on this visualization, one model designer pointed out that whenever 2 criteria need to be balanced, scatter plots are his visualization of choice, simply because from the bending of the Pareto front, he can directly see how much losses in one criterion need to be traded for a certain gain in the other criterion. However, most optimization scenarios typically come with more than 2 criteria. And for those cases, the domain experts particularly appreciated that they could view all available design options while simultaneously observing all criteria. And then one of them also wished to see the underlying 3D models of the motor designs. And finally, there was one other participant who stressed that he could imagine the visualization to be used not only for the decision itself, but also for presenting it to the customer to verify the decision together with them. Now, being able to optimize and choose a variant of a single unit is already quite helpful for many applications. However, many subject to decide upon are actually systems where multiple components are operated together. So as a simple example, let's consider a camera body and a lens. So deciding for a camera body rules out lenses due to different mount types. And then the performance of the camera body and the lens can only be judged with both items together. So before, this kind of codependent choice was approached in an iterative manner. So you start with one component, choose the most preferred variant of it, then use its properties for the choice of the next component, for example, to check for interoperability or the joint performance. Then you might realize that you cannot achieve your desired optimization goals. So you go back to the first component, choose the next preferred variant, and repeat the remaining choices. So all in all, a rather tedious and maybe at times also frustrating trial and error process. And as a consequence, decision makers might tend to proceed with a first working solution rather than striving to find even better designs. So what can we do to help with this kind of codependent choices? So to support a simultaneous exploration of multiple components, we developed a novel visualization technique, which is again based on parallel coordinates, as they have already proven successful. So this time, we place multiple parallel coordinates plots on top of each other. So one plot for each component involved. And this is to remain capable to analyze variants of individual components on their own, just like before. And then the special thing is that those parameters that refer to both components, for example, the mount type in the camera example, or costs, they are placed directly on top of each other, basically in one vertical line. And then to analyze the joint performance of both components, these parameters can be merged into so-called composite axes. And these composite axes can either depict interoperability, for example, do the components have the same mount type, or they can depict joint criteria like the total costs of camera and lens together. Now, let me give you a slightly more complex example of a magnetic geared motor. So here, the two components are arranged side by side. next to each other within the common housing. So motor on the left and gear on the right. And this is, I need to hold it like so. This is what it looks like from the outside. So you have the motor here and the gear here. And then motor and gear share a high-speed rotor, which means that the outer diameter for this rotor should be the same for both components. And the components are also connected via their gear ratio, which is given between the shared high-speed rotor and the output rotor, which is located in the gear. So these are the dependent design parameters. And then we also have dependent criteria that represent the overall performance of the entire magnetic geared motor. So here, for example, as motor and gear are arranged side by side, we can approximate the construction volume by simply adding up the individual lengths of both components. Now, what does that look like in the visualization? So here we have gear variance in purple on top and motor variance in green at the bottom. And then in the center, we see the shared design parameters, rotor diameter and gear ratio. And then next to them, we see a composite axis, which depicts the total length of combined motor and gear variance. And next to that merged axis, we can see an axis pair with a small plus sign in between. I hope that you can see it, which means that the individual losses of the components can be merged via addition to view the total losses of the system. Okay, let me try to demonstrate that in a short demo as well. Okay, so here we have the visualization. So the primary objective is to minimize the power loss of the entire system. So first we need to merge the losses of both components by adding them up. And now here with the shared design parameters, we can see the different configurations of the system. So combinations of diameter and gear ratio. So if we hover through them and observe the total losses, we can see, well, here the range is covered. And here we have a rather smaller cluster, narrow cluster of system variance resulting in rather mid-range losses, which is quite special. But now we will go back to the total losses and apply a constraint. So we will simply restrict the losses and see what happens. So if you observe the separate pathways, which depict the individual component properties, we can see that there was not that much of an influence, so we can still choose among the entire ranges of individual properties. And then the second objective is to minimize the construction volume. And I already said we can approximate the construction volume by adding up the individual lengths. However, to filter for that, it is more meaningful to do that at the component level, because otherwise we could not identify combinations where the total length itself is acceptable, but the individual motor and gear lengths differ significantly, which is not desired. So we do that at the component level and restrict the length for each component on its own. And again, see what happened. What is now striking is that here, this entire cluster of gear variants, because it's a purple axis, gear variants with low magnetic flux density, which is desired, have been removed from the selection. So we might ask, where did that come from? How did that happen? So if I try to loosen this restriction on the overall losses, then we can see that slowly these variants move back into the selection. And then we could say, well, okay, let's investigate this correlation from the inverse perspective. So let's just filter for low magnetic flux density. And what we can see here now is that the system variants with low losses, total losses, have been again excluded. So what we have here is a relationship or a conflict between a component level criterion, so the magnetic flux density of the gear, and a system level criterion, so the total losses which were added up. Now, what we can also see is that for the configurations, we have one combination here with higher rotor diameter, but as you can see on the axis of the total losses, it results in rather high losses, at least highest losses from the selection. So this one might not be that desired. So we might conclude that this configuration with a rotor diameter of 21 and a gear ratio of 18 might be superior, might be from these four configurations the superior configurations. And this is also what the engineers found and also reported in their publication. So we would like to continue with this selection. So I would lock it by clicking on the polyline section to be able to interact with the remaining polyline sections. Because once I move the mouse from this polyline section, the selection will be gone. So I need to lock it. And now what we can see here is one outlier kind of in the motor lengths, which actually results in the lowest losses from the remaining selection. So I hope you can see that when I move back and forth. So what we might conclude is that this motor variant might be our motor design option of choice. And the only question remaining is with which of these remaining gear variants it should be combined, right? But that's for another day. So if you're interested, we can dig deeper into that. Okay, now we'll go back to the presentation. So to conclude, I am convinced of the potential of visualizations, the potential that visualizations offer in assisting multi-attribute choices, and that moving towards this goal will contribute significantly to different research topics that we are dealing with in the visualization community. So to summarize, in the first part, I showed some characteristic properties of multi-attribute choices that call for visualization support and what challenges they also bring to our visualization research. And then in the second part, I showed some examples from past research projects, one on eliciting domain knowledge and two projects from model design regarding single choices as well as codependent choices. So the research directions we are pursuing are to further investigate multi-attribute choices in the wild, so using well-known design study methodologies, thus moving from the current rather artificial settings more towards real-world settings, to develop more validated visualization techniques to make trade-offs and even more complex choices involving mutual effects, like in this case, or also uncertainty, which had not been possible before in this extent, and to continue learning from related disciplines like cognitive science or decision theory, which offer a long history already of studying how humans think and make decisions. Now, if I could name some thoughts that I would like you to remember from this talk, it would be first that multi-attribute choice is an important, sometimes underrated task. And there is still so much for us to discover in researching dedicated visualization support. So in line with this visualization, we need visualization research to not only focus on analytic tasks as the building blocks of choices, but to treat choices as a task on their own. And finally, we should acknowledge the subjective nature of choices along with its strength and also weaknesses, and push forward our fundamental understanding of making choices as humans and assisting these choices with interactive visualizations. So I would like to end my talk with a very short introduction of my research environment. So as a PhD candidate, I am affiliated with the TU Darmstadt, but my everyday research actually happens at the Fraunhofer Institute for Computer Graphics Research, IGD. So Fraunhofer itself is an organization for applied research with currently 76 institutes across a diverse range of disciplines. And at Fraunhofer, we operate at the intersection of science and industry. So we basically build the bridge between universities and companies. And the focus of our institute in Darmstadt is visual computing. And in our department in particular, we are researching information visualization techniques to empower humans in various data analysis settings. So from engineering over cybersecurity to medical applications. So with this, I would like to thank you very much for your interest and time. Fortunately, as Mark already said, I do not have to leave Linz just after this talk, but I will spend the next 2 months here. So if you would like to catch up afterwards, either today or in the following weeks, just contact me and I would be happy to further discuss. Thanks.
Thanks a lot for this great talk, great storytelling and very nice demo. And I think the fact that we have so many domain experts here from LCM also shows interest in your work. Okay, we have time for a few questions. Who wants to go first? By the way, we also have like an online crowd of about 20 people on the Zoom call, and further we're like on the YouTube channel, which we don't know how many out there, probably millions. Okay, questions. Who wants to go first? Yeah, Klaus.
Okay, thanks for the talk. For the second paper you showed, composed, for the axis where you visualize a value for both components, are the other lines always coming together to a single point on the axis? It's a joint.
Yes, I will put up the slide again. Yes, exactly. So at this joint axis, they will meet, and this is also the reason why there are so many lines here, although we have not as many here because the individual variants are combined, and they can be combined not only one by one, but also one to many, depending on what the design parameters specify for the interoperability. So for example, here we have assumed that the rotor diameter should be the same. You can also apply any other Boolean function there, or even other functions that specify, for example, a certain tolerance or something. So how exactly the variants meet there depends on what function you put on the merge axis. So what function you use for composition actually.
Thanks.
Okay, we already have one question online, asked by Wolfgang Eigner, a colleague at University of Applied Sciences in St. Pölten. Wolfgang, do you want to unmute yourself, or should I read out the question?
Sure, I'm happy to. Hope you can hear me.
Yes,
yeah.
Perfect.
Perfect. Thank you, Lena, very much for the very interesting presentation. I have a question for the first part where you introduced the critical decision method. I think you mentioned it briefly, but I wanted to ask about, do you know, or have you used any like structured ways to model and store the knowledge that you find by this method?
Yeah, so we up to now, we use the artifacts that are suggested by the original works from cognitive science. So that would be these two artifacts. But of course, this is only, well, you can consider it a suggestion because, of course, depending on what exact type of cognitive aspects you want to elicit, there might be other representations which might be more applicable or more meaningful. So I think we should not, well, see that as an imposed kind of representation, but rather use it as for inspiration, and then decide for a representation that suits the research question best. So does that answer your question, Walker?
Yes, thank you.
Okay, cool, perfect.
Okay, more questions? Yeah, Andreas.
Thanks for the talk. I'm personally interested a lot in dimensionality reduction. And since this is kind of an exploration of a high dimensional science space, right? Do you have any experience if domain experts use dimensionality reduction? Do you think it could be an alternative to parallel coordinates?
I don't want to speak for them. Maybe we can ask them later, but for my understanding, it kind of depends on what exactly is the requirement for the domain problem. So when talking to engineers, I often made the experience that it is important at some points in the analysis to really be able to view the actual raw values and to be able to relate them. So I think you would need to adjust dimensionality reduction methods to that requirement, but I don't know, maybe you have some, would you like to speak for yourself, maybe? Not really, okay.
The problem is we don't know this, how it works.
Okay, so yeah, maybe it's also yeah, a question of knowledge gaps.
Yes.
Or, yeah.
So dimensionality reduction, the visualization would be a scatter plot basically, where the axes have no meaning, and just how close 2 points are describes the similarity in high dimensional space. So it could be a nice overview of showing like a cluster of simulated results that have common or similar properties, that share properties. But we could also look at that together. Yeah, I think it's
Must sound interesting.
okay. I have one question. So does it always make sense, or can domain experts always make hard filters, or can you account for this uncertainty with like fuzzy filter? Yeah. Account for this uncertainty?
We have already talked about that. So that was one point also that we discovered in the evaluation, that in case of rather soft constraints, or where it really is a question of balancing and trading off, so that's the task itself, right? So these hard constraints, they make it easier to achieve a subset, but then at some point you will have to balance criteria, and there it makes sense to have some kind of fuzzy brushing or smooth brushing. I think we already have that in the visualization community, to be able to account for this type of uncertainty, or to not have this 1 or 0 membership. Yeah.
And could you also have something like weights on the different attributes or choices? Because some might be more important than others, right? And now they are all.
Yes. Let me go back to this. Where do I have it? Design rationally. So we thought about adding weights to the criteria. I know also that approaches exist that based to large extent on that idea. Our idea was that domain experts should not be forced to specify weights too early. So the idea was to rather allow them explore the options and then apply constraints like on the go. So whether to apply weighting is basically a matter of this third rationally, where we have objectivity versus guidance. So adding weights, or also depicting important axes maybe to the left, and then having less important access, maybe out of the screen, only accessible via scrolling or something. There would be some kind of guidance, but we in this case valued objectivity, because we said, like, initially we cannot tell whether criteria are more important than others. And in our cases, maybe that also showed a little bit in the demo, we kind of apply weights in the sense that the more important criteria are processed first. So I said, like, the major criteria are this and that, and then we started to filter on these first. So it is mainly up to the domain experts, to the engineers, to the user to interact in that way.
There's a second question from Wolfgang. Wolfgang?
Yes, thank you. I just wanted to bring in maybe another perspective, as you have this like very complex and multi-attribute decision-making processes here. So would these tools be usually used by a single analyst or rather cooperatively for a decision-making process?
Question, Wolfgang. Really, thank you. Because for PAVED, we only had single analysts in our evaluation case studies, but for Composed, we actually had a pair of analysts, of domain experts, try out the tool and also talk to each other. And it was really interesting. We were really surprised by how, like, what quality of insights we could get by seeing how they learn not only from interacting with the data, but also from interacting with each other. So I think that this is really something that we maybe should do more or try out more. So in this case, this really turned out to be beneficial. And the engineers also reported that these kind of decisions are not necessarily made on their own, but often you have a second expert besides that. And we also realized that this was it looked a little bit like pair programming. So you had one expert who kind of steered the visualization and interacted with that, and then you had the second expert who pointed at what might look interesting or commented on what happened there. So you had one driver and one observer, if you want to say that.
Yes, I also thought about like maybe like introducing some more cooperative interactive environments that would allow multiple people to actually interact with the representations, but might be an interesting avenue.
Yes, we also talked about that, but in our case, the domain experts didn't want that, because they said it is not about like doing things in parallel or speeding things up, but rather it is about really, taking the time to explore the options, and two experts, but one only interacting with the visualization.
Interesting. Thank you.
Okay, thank you for all the questions. In the interest of time, I have to close the session now, but there will be plenty of additional opportunities, maybe at Mensa or you name it. Okay, and just an announcement, our next talk, so we're skipping February as this is the semester break. We're going to have a follow-up talk given by Michael Burg from FH Graubünden in March. And yeah, for those of you who are students part of the seminar in the IE and you are here, please let us know so that we can take your name. And with this, I want to close the session. Thank you everyone for joining us, and have a great rest of the day. Thank you.